An ultra-low energy building envelope relies on extreme insulation and uncompromising airtightness to isolate the interior. It forms a barrier that blocks solar radiation and outside air temperatures, perfectly keeping external sensible heat from entering the structure. But humans operate biologically. Occupants generate a continuous influx of latent heat, specifically moisture from respiration and perspiration. Furthermore, these airtight buildings require mechanical fresh air ventilation. In a tropical climate, that intake air continually introduces massive amounts of external latent heat. Inside a perfectly insulated, perfectly sealed box, these constant latent moisture loads have nowhere to go. They rapidly accumulate. The standard response from HVAC engineers is to assume that because the building is well insulated, it simply requires a smaller, lower tonnage conventional air conditioner. Perfecting insulation without a specialized method for managing that latent moisture creates a severe psychrometric hazard. The space becomes a trap for humidity. This chart compares a standard building's thermal loads to a passive house. The key is the sensible heat ratio, sensible divided by total cooling load. Conventional buildings operate at 0.8 SHR. By stripping sensible heat, a passive house drops below 0.5. Inserting a conventional air conditioner into a low SHR building guarantees mechanical failure. The hardware is inherently designed to solve a 0.8 environment. Our universal comfort target in hot climates is exactly 25 degrees Celsius and a humidity limit of 12 grams per kilogram. In standard buildings, cooling starts at a hot, humid state, like 30 degrees and 80% relative humidity, and pushes leftward toward that target. Because the sensible load is massive, the compressor runs continuously. It wrings out the indoor moisture by accident, a process known as dehumidification by chance. In a low SHR passive house, the context changes entirely. The sensible load is near zero. When the system turns on, the thermostat is satisfied almost instantly. The cooling process stops abruptly at 25 degrees, but the air still hovers far above our 12 gram per kilogram limit. This causes short cycling. The compressor shuts off long before condensation can even form on the cooling coil to extract the water. The moisture is trapped. Relative humidity spikes past 80%, triggering an immediate risk for mold growth and structural damage. Relying on dry bulb temperature sensors to control indoor moisture in an ultra-low energy building will always fail. To actually remove moisture, physics dictates a strict rule. Air must be cooled below its specific dew point. The dew point is exactly the temperature at which airborne water vapor instantly condenses and transforms into liquid water. This chart shows that reaching our 12 grams per kilogram target requires the cooling coil to aggressively drop the air temperature down the saturation curve to roughly 15 degrees Celsius. That 15 degrees supply air is then pumped into a space that has almost zero external heat penetrating the walls to offset it. The occupant experiences the overcooling trap. The absolute humidity reaches the correct level, but the room becomes freezing and thermally uninhabitable. Successfully reaching the humidity target using pure sensible cooling breaks the thermal comfort requirement entirely. To solve this, sensible cooling and latent dehumidification must be mechanically decoupled. Looking at this chart, decoupling requires a two-step psychrometric process: sub-dew point cooling to extract the water, followed by an immediate temperature recovery back to the comfort target. This schematic shows the first hardware configuration capable of doing this: a dedicated drying mode using a secondary throttling valve. It redirects hot refrigerant gas from the exterior condenser to an interior reheat rail. This redirected gas warms the painfully cold air back to a neutral temperature before it enters the room. A second passive hardware configuration is the wraparound heat pipe. It pre-cools incoming warm air across the pipe and transfers that exact thermal energy to post-heat the exiting air. The heat pipe leverages the incoming air's own thermal energy to execute the reheating phase, requiring zero additional compressor power. The mechanical output of either system is neutral temperature, fully dehumidified supply air that will not overcool the space. Active reheating transforms dehumidification from an accidental byproduct of cooling into a precisely controlled, independent variable. Active reheating solves the indoor air, but to make the system efficient, we must reduce the latent load before it ever reaches the cooling coil. The enthalpy recovery ventilator, or ERV, acts as the mechanical gatekeeper for all fresh air entering the building. An ERV is a system that exchanges stale indoor air for fresh outdoor air, while transferring heat and moisture between the two streams. This diagram shows the physical mechanism inside an ERV. High humidity intake air crosses a rotating desiccant wheel or a permeable membrane. The extreme exterior moisture is absorbed and transferred directly into the outgoing exhaust air stream without the two air masses ever mixing. This rejects up to 60% of the ambient absolute humidity back outside before it touches the active cooling coil. Without this massive latent load reduction acting as the first line of defense, efficiently cooling an ultra-low energy building in a humid climate is mathematically impossible. To validate these mechanical solutions, engineers model the building's specific loads using tools like the Passive House Planning Package, or PHPP. During this phase, designers cannot rely on standard energy efficiency ratios, or EERs, provided by equipment manufacturers. Because factory EERs are tested under moderate European or US conditions, they completely fail to predict latent capacity in tropical environments. This interface shows the required adjustment. The equipment's EER must be strictly reevaluated at the actual operating target of 25 degrees Celsius and 60% relative humidity to ensure it can handle the load. When correctly specified, an optimized combination system utilizing an ERV and active reheat operates with an incredibly low energy footprint, drawing roughly 10 watts of cooling power per square meter. It resolves both sensible and latent loads using a mere fraction of the power required by conventional buildings. Extreme climates demand high-precision mechanical responses. To match an ultra-low energy envelope, conventional air conditioning logic must be permanently abandoned.